Hi, welcome to our case study presentation for the TIT6223 IoT Fundamentals. Today we are here to present our case study, which is the Public Restroom Availability Monitor. This project was developed by our group, including me and my partner, Ding Tak Seng. We have designed this system to address a common yet overlooked issues in facility management, which is the inefficiency and hygiene risk associated with checking restroom occupancy in high-traffic public areas. So to guide you through our work, we have structured this presentation into logical phases. I will be responsible on presentation by covering the first three key sections, which is the literature review, part 1, the project proposal and system architecture, and part 2, the detailed system design. Once I have established this technical foundation, I will pass the floor to my partner to demonstrate the following parts, including the implementation, the data analysis, and conclusion. So let's begin with the literature review. Alright, so now let us move on to our first part, which is the literature review. So I will begin with the literature review, where we analyze the evolution of facility management to justify our project. Traditionally, public restrooms are managed using fixed schedules and manual inspections. Our review of current research highlights that this method is fundamentally flawed. It fails to address dynamic occupancy, which means that cleaners often clean empty stores while missing overcrowded ones. Furthermore, in the post-pandemic era, manual checking posed a severe hygiene risk by forcing users to touch door handles. We also found that while some early IoT solutions exist, they were often implemented in what researchers call a silo fashion, means that they lack the centralized data aggregation need for facility-wide analytics. This identifies a clear need for a system that connects individual store monitoring to a central cloud dashboard. So next, we will evaluate the hardware. System reliability depends entirely on sensor choice. While passive infrared motion sensors are popular in literature, our review found that they suffer from a critical limitation, which is false negative. If a user sits motionless inside a store, a PIR sensor often reports the store as empty, leading to embarrassing errors. So to solve this, we select a magnetic contact switches. This provides a binary accuracy by detecting the mechanical locking of the door rather than human movement. It is cost-effective and crucially non-invasive to privacy. We also adopt the architecture model of edge cloud collaboration. This means we process the data locally on the microcontroller to trigger the LED light immediately, minimizing network load and ensuring the system works even if the Wi-Fi temporarily drops. So for connectivity, we perform a comparative study of wireless technologies. We analyze LP1 protocols like LoRaWAN. While they have a great range, they suffer from high latency and low data rates, which making them unsuitable for a system that requires instant red light or green light updates. We also reject Bluetooth due to its short range, which is not scalable for monitoring from a distant management office. We conclude that Wi-Fi is the optimal protocol for indoor environments like malls and airports. It leverages existing infrastructure, reducing deployment costs. Most importantly, it offers a latency of less than 10 milliseconds. While literature notes that Wi-Fi consumes more power, this is not a disadvantage in our case, as public restrooms have readily available mains electricity. So last, we will synthesize these findings to identify the research gap. So we found that many developed solutions prioritize high-tech automation, such as robotic cleaning or medical health analysis, which are impractical for widespread public use. On the other hand, cheap solutions often lack data logging capabilities. Our project bridged this gap. We proposed a hybrid system that balances cost and functionality. We combine accurate magnetic sensing for the user experience of finding a store with robust TCP/IP connectivity to provide operational data for managers. This connects high-level theoretical model with a real-world and deployable solution. So next, let us move on to the part 1 of this case study, which is the project proposal and system architecture. So first is the problem statement, which we have the issue of inefficient manual verification. Currently, The only way for a user to know if a specific store is available is through what we call the try and error method. This forces users to physically walk down corridors, push on the store doors to see if they are locked, or even resort to bending down to check for feet under the door. This method is not just efficient, it is a direct invasion of privacy. It creates significant anxiety for the user inside the store who worries about the door being pushed open and leads to awkward social interaction for the person waiting outside. The lack of clear visual indicators result in a poor overall user experience. Second, there is a serious public health and hygiene risk. We know that public restrooms are environments that contain high levels of surface pathogens, including bacteria and viruses. Studies show that door handles and latches are among the most frequently touched surfaces in these facilities. By relying on manual checking, we are forcing every user to touch this handle unnecessarily just to find an empty store. In this era, which health awareness is crucial, this lack of contactless navigation increases the risk of cross-contamination and disease transmission between users. So finally, we must consider the operational inefficiency. From a facility management perspective, the lack of real-time occupancy data creates chaos. Without guidance, queues tend to form unevenly. Users crowd the entrance or wait the first few stalls, often leaving the real store empty and unnoticed. This also impacts the cleaning staff. As mentioned in our report, cleaners currently operate in a blind state because they cannot easily identify which store needs quick cleaning without knocking or waiting. This will disrupt their workflow and makes it difficult to optimize cleaning schedules based on an actual traffic. Next, move on to the proposed solution. So based on the problem we've identified, our proposed solution is an IoT-based public restroom availability monitor. The core objective of this system is to automate the detection and visualization of store occupancy. We aim to replace the traditional unhygienic manual checking method with a smart sensor network that allows users to identify free space directly from the restroom entrance. So we designed this solution to be non-invasive, which means that we don't use cameras. So it will respect user privacy while being easily scalable for large facilities like shopping malls or airports. So how does the system operate locally? Okay, the system starts by installing a magnetic contact sensor on each store door. In our Cisco packet tracer simulation, this is represented by a toggle switch. The logic is simple but effective. When a user locks the door, the sensor completes its circuit and sends a signal to the central microcontroller. The microcontroller immediately processes this logic to control the local indicators. Outside each specific store, a red LED will light up to indicate occupied and a green LED will indicate available. So, furthermore, to prevent users from walking in unnecessarily, there is a central LCD screen installed at the main entrance. This screen provides an immediate summary which provides users instant guidance before they even enter the facility. So beyond the local hardware, we utilize IoT connectivity to improve facility management. The microcontroller is connected to a home gateway using the Wi-Fi protocol. This allows the system to transmit real-time occupancy data to a remote IoT server and a smartphone dashboard. This connectivity solves the core problem we discussed. So first, it creates a fully contactless navigation experience which improves hygiene since users do not need to touch door handles to check availability. Second, the data collection allows facility managers to remotely monitor usage patterns. This enables them to optimize cleaning schedules based on actual traffic instead of relying on inefficient fixed time intervals. Now, let us look at the high-level system architecture diagram, which shown in Figure 1.1. To ensure the system can handle user guidance within the restroom while simultaneously processing data for remote management, we organize the architecture into 5 different layers. This layer approach facilitates a seamless flow of data from physical input to the final outputs. The flow starts at the sensing layer. This represents the physical environment we are monitoring. Each store is equipped with a magnetic contact sensor, which is represented as a toggle switch in our Cisco packet tracer simulation. This sensor detects the locking mechanism of the door. When a user locks the door, the sensor completes the circuit and transmits a raw digital signal up to the next layer. So next is the processing layer. The component here is the central microcontroller, or what we call is MCU. This acts as the decision-making unit of the entire system. The MCU continuously receives the digital inputs from the sensors to determine the real-time occupancy status of each specific store. Once the decision is made, the MCU triggers the actuation layer. This layer provides immediate visual feedback to user inside the facility. By using general purpose input-output, or what we call is GPIO control signal, the MCU activates the store indicators, which turning on the red LED if occupied or green LED if available. Importantly, the MCU also aggregates the data to calculate the total number of available stores. It transmits this data through serial or 1 I2C communication to the central LCD screen installed at the entrance. This ensures users receive guidance without needing to connect to a network. To achieve IoT capabilities, we extend to the network and cloud layers. The MCU utilizes the IEEE 802.11 standard, which is the Wi-Fi protocol, to create a wireless connection with the local home gateway. So this gateway bridges the local network to the wider internet, forwarding the occupancy data through a wire Ethernet connection to the IoT registration server. This server acts as our central database and cloud platform, logging every status change and storing historical usage data. So last, we have the user interface layer. This allows for remote access. Facility managers can use their smartphone or tablets to monitor the restroom status from a distance. This device communicates with the IoT registration server through HTTP requests to retrieve the latest data and display it on a digital dashboard. This complete architecture loop ensures that we not only solve the queuing problem for visitors, but also provide a valuable operation insight for building management. So next, I will explain our two-chain justification. For this project, we select a simulation-based methodology rather than using physical hardware. The primary reason for this choice is its scalability and replication. A realistic restroom monitoring system is not just a single device, it requires multiple similar sensors nodes to cover 3 to 4 different stores simultaneously. So to physically create this, we require purchasing multiple sets of microcontrollers, sensors, and wiring, which significantly increase cost and hardware complexity. By using simulation, we can immediately replicate this node without physical resource constraints. This approach also allows us to focus our efforts on the system logic and integration. So instead of spending time troubleshooting loose physical connection or power supplies issues, we could focus purely on the code and the data flow. Within the simulation aspect, we specifically choose Cisco Packet Tracer. This selection is important because unlike basic circuit simulators that only focus on the component level, like simply connecting a single LED, Cisco Packet Tracer simulates a complete and converged Internet of Things ecosystem. This is vital for our specific case study because our solution is not just about turning on lights. It involves transmitting data from a local environment through a home gateway to a remote network. So, this Cisco Packet Tracer is the only tool that allows us to simulate both the physical layer and the network layer within a single and unified workspace. So finally, this toolchain addresses the challenge of facility visualization. Our project needs to demonstrate the interaction between components in different physical locations, the separation between the store, the entrance display screen, and the remote management office. Cisco Packet Tracer allows us to logically group these components into visual areas. This macro-level visualization provides a clear proof of concept that demonstrates how the system runs in a real-world building infrastructure, which is a perspective that very hard to achieve using a standalone hardware kit or code-only platform. So next, let us move on to the last part of my presentation, which is the part 2, detailed system design. So first, let's look at the bill of material for the prototype. The table 2.1 shows the specific hardware components required. We focus on components that offer the best balance of connectivity and accuracy. First, the core and sensing components. We select the ESP32 Wi-Fi microcontroller instead of a standard Arduino because it has built-in Wi-Fi. This is important for transmitting data to the server without buying expensive add-on modules. For sensing, we use the wired magnetic reed switch model MC38. Unlike motion sensor which can trigger falsely, this acts as a business binary switch as it only completes the circuits when the door is physically locked, which ensure high accuracy. Second, for the visual feedback, we use a 16x2 LCD display equipped with an I2C adapter. This adapter is crucial because it allows the screen to work using only two data wires, which free up the microcontroller's pin for other sensors and LEDs. We also utilize standard red and green LEDs for immediate status indication. So last, the support components. To build the prototype, we include a breadboard and jumper wire kit for solderless circuit assembly. We also use a 5V power adapter to convert raw power to a stable DC output. This ensures the system can run continuously in a public facility without the maintenance issue of changing batteries. The total estimated cost for this hardware setup is between 77 to 88 ringgit. So in addition to the prototype hardware, we must consider the network environment. The table 2.2 shows the existing network and user infrastructure. In real-world scenarios like shopping malls or airport, this infrastructure is usually already in place. Therefore, these items are counted as existing assets rather than purchased items for our project. So first, regarding the network, the system is designed to connect to a standard wireless Wi-Fi router. This allows us to utilize the built-in existing Wi-Fi network, eliminating the need to install a separate router inside each restroom. So similarly, for the back-end, we utilize the IoT registration server. This acts as the database to store occupancy logs. So by using existing building servers or free cloud platform, we ensure the solution is scalable without high maintenance costs. So last, the mobile smart device. This represents the interface used by cleaners or facility managers. Since our system provides a web-based dashboard, it is accessible on any standard smartphone or tablet. This allows us to leverage a bring your own device, which is known as BYOD model, meaning the facility does not need to purchase dedicated monitoring screens, further reducing the overall hardware costs. So moving on to section 2.2, the detailed data flow diagram. The figure 2.1 shows the level 0 data flow diagram. This diagram traces the path of data packets from the physical sensor all the way to the end user, highlighting the process decision made at each stage. The flow starts at process 1.0, where the physical layer meets the digital system. When a restroom user operates the door lock of a store, this physical action will trigger the magnetic contact sensor. The primary function of this process is to collect data and convert the mechanical movement of the lock into a raw binary input signal. This allows the microcontroller to read the environment without needing any manual input. Next, the signal passed to process 2.0, which acts as the central logic engine. Here, the microcontroller uses Boolean logic to analyze the input. If the signal shows a closed circuit, the system marks the specific store IDs as occupied. If it shows an open circuit, it marks it as available. So importantly, this process converts the electrical signal into usable status data and divides it into two parallel streams. One stream for immediate local execution and another for remote logging. So following the local stream, we reach to the process 3.0. This process handles the hardware actuators inside the restroom. After receiving the status data, it sends a voltage signal to the specific LED indicator to provide visual feedback. So red for occupying and green for available. Simultaneously, this process aggregates the data to calculate the total count of available seats. It updates the local LCD screen at the main entrance, ensuring that users receive real-time guidance even if the network goes down. So finally, the flow extends to the remote network in process 4.0 and 5.0. So process 4.0 is responsible for managing remote communication. It encapsulates the status data and transmits it via the Wi-Fi gateway to the D1 status log, creating a historical record of the usage. So process 5.0 then checks this real-time data and generates a visualization on the remote dashboard. This allows the facility manager to monitor the restroom status seamlessly through their phone or tablet by using HTTP requests. So in addition to the data flow, this figure 2.2 illustrates the system logic flowchart. This outlines the specific algorithm executed by the microcontroller in an infinite loop. This logic starts with initialization and sensing. After powering on, the system initializes the network connection and configures the GPIO pins. It then enters an infinite system loops where it reads the sensor. The microcontroller pulls the digital status of the sensor connected to store 1, store 2, and store 3. This ensures the system gets complete and accurate information about the restroom occupancy before making any decisions. The main intelligence is demonstrated in the decision chain. This code executes a specific logical check to each store to see if it is occupied. So if the condition is true, which means that the lock is closed, then the logic will follow the yes path. It triggers the occupied status, turning the red LED on and the green LED off. So if the condition is false, which means that the lock is open, then the logic will follow the no path. It will trigger the available status by turning the green LED on and the red LED off. So this structure is repeated for every store, ensuring the visual output always matches the physical reality. So last, the loop ends with data aggregation and transmission. After determining the status of all stores, the system creates a format data string. It uses this packet to update the text on LCD screen and simultaneously transmit it to the IoT server for remote logging. Importantly, the flow ends with a 500 ms delay before looping back to the start. This is important because it prevents the microcontroller from overloading and ensures that our data transmission meets the network stability standards. So let us move on to the section 2.3, communication protocol selection. Our protocol stack choice was driven by the need to fit into current indoor infrastructure while providing data integrity in real time. Consequently, we select a hybrid solution using Wi-Fi for the network layer and HTTP over TCP/IP for the application layer. First, for the network layer, we choose Wi-Fi. This decision was based on three key factors. First, the infrastructure compatibility. Unlike agriculture environments that need LoRaWAN, our target environments such as malls, airports, and universities already have robust Wi-Fi systems. By using existing access points, we can significantly reduce deployment costs and eliminate the need for installing proprietary gateways. So second, the bandwidth and latency. Real-time performance is critical. A user standing at the entrance needs to know immediately if the store becomes available. Wi-Fi provides high data throughput with negligible local latency of less than 10 milliseconds, preventing the issues of stale data often seen in slower mesh networks. So the third is power availability. While Wi-Fi consumes more power than BLE, this is not a concern of us. Mains electricity is readily available in Restroom, allowing the MCU to run continuously without battery constraints. Second, for the application layer, we utilize HTTP over TCP/IP. So we specifically choose the transmission control protocol TCP instead of UDP because data integrity is paramount. We cannot afford to lose a packet that says a store is occupied. TCP provides a handshake mechanism and error checking to ensure that the server database always matches the physical status of the store. We also use HTTP as the native language. This ensures that the system is platform neutral, meaning facility managers can use standard GET requests on any device with a web browser to view the dashboard without needing to install a specific mobile application. So to ensure we made the best architectural decision, We evaluate alternative protocols using the comparison matrix shown in table 2.3. So first, we evaluate Bluetooth Low Energy (BLE). While BLE is energy efficient, it was rejected due to its limited range of approximately 10 meters. In a large facility, the management office might be located on a completely different floor from the restroom. So using BLE will require a complicated and expensive network of repeaters or a specific smartphone to connect locally, which is simply not scalable for remote monitoring. Second, we evaluate the LoRaWAN. Although LoRaWAN offered excellent range, it was rejected because of its low data rate and latency. LoRaWAN is designed to transmit small packets at infrequent intervals. However, our system needs to update immediately the moment a door is opened or closed. The latency of LoRaWAN is too high for this application, and frequent transmission will congest the network. So therefore, as shown in the matrix table, Wi-Fi remains the only suitable choice that balance indoor range, high data rates, and compatibility with existing infrastructure. Alright, so that's all for my part. Thank you so much.